In this lecture, we'll introduce the principle of mathematical induction. So this is a powerful proof technique, but it's used in sort of one specific, specific but common situation. So it's used to prove statements for all the natural numbers, statements about all natural numbers. So for all, and in the natural numbers, something, right? This is a common situation. For example, it could be so it could be something like a little formula. Here's an example statement. So the sum of the first, let's say, n numbers, natural numbers. I'm using 1 to be the first natural number, but you can consider 0 to be the first if you'd like. It doesn't really make much of a difference. But yeah, there's this famous sum formula. So the sum of the first n natural numbers is given by n times n plus 1 over 2. And this works for any n. So induction is the way to prove something like this, or it's one of the ways to prove something like this. So here's a general setup. So suppose we're given statements where we have propositions for each n. So for each natural number we have a statement, and like a formula like this sort of comes with a statement for each natural number. So we would call them proposition 1, proposition 2, etc. P3. So you have a bunch of propositions or statements. Okay, I'll stop now. Like for example, in this statement, P3 would be not equals, but it would be 1 plus 2 plus 3. The claim is that that's the same as 3 times 4 over 2, which it is. 6 on both sides. So, but how would you actually prove something like this for all natural numbers? Well, that's what induction is sort of set up to do. And the idea is a fairly simple one. And at first, it almost seems too simple. Like it seems like it should not work. But here's the idea. You start by proving one of them. Usually the first one is the one you want to prove. So prove the first statement in line. Prove P1. Okay. And then the second step, I'm going to do it for this example in just a second, but I just want to outline the idea first. So the second step is that you assume that pk is true for some k. Assume p. So assuming pk is true, where k is arbitrary, just any natural number. This has to be greater than the first one you picked, greater or equal. Assuming that's true, show that the next statement in line is true. Okay, I'm not proving I haven't proved that pk is true. I'm just assuming that's true, and if I do assume that, I need to actually prove that the next one is true. Okay. So what am I really doing? In other words, I'm proving an implication, right? So in other words, prove the implication pk implies pk plus 1. Right? That's what I'm really doing. So how do you prove an implication? Well, you assume that's true, and then you show that's true. So you prove that implication, and then I think there's a step 3, but actually that's it. So you're done. You've actually proven the statement for every natural number, all infinitely many of them. So you've proven the statement. You've proven the statement for all natural numbers. Okay? Why is that the case? It seems like we only did one thing, right? We only proved it for one number, but that's not really what we did. We assumed it was true for one number, and then assuming that, where that was an arbitrary k, right? Assuming that, we showed it's true for the next number. So for example, in this chain here, assuming p of 4 is true, we don't know if it is or not, but if it is, we were able to prove p of 5 is true. But is p of 4 true? I don't know. But assuming p of 3 is true, we can prove p of 4 is true. And then that would prove that p of 5 is true. And then p of 6 is true, and p of 7 is true, right? And so as long as this chain is able to start somewhere, so for example, p1, we actually have to go in there and prove it, right? So p1, if that's true, that implies p of 2 is true. But assuming p of 2 is true, that implies p of 3 is true, etc. And we have an unbroken chain, right? K is arbitrary here. So that's the idea. It's really a beautiful idea. So this step here is often called the base case. It's what the whole thing is based on. So if you don't have a base case, if you never actually proved it for any number, well, then we don't know if it's true for any numbers or not. But as soon as we have that base case, this second step, which is called the inductive step, I need to get better pens, it looks like. But in any case, yeah, so the inductive step, that's going to prove it for all natural numbers. Okay. Let's do this for this example, just so we can get a feeling of how this works. So, yeah, example. So the one above. So prove the formula. 1 plus 2 plus 3 all the way up to n is n times n plus 1 over 2. Very useful formula. For example, if you want to add up all numbers from 1 to 100, you can do it in a few seconds with this formula, right? It's 100 times 101 over 2. 100 over 2 is 50, so 50 times that is 5,050. So that was very quick. A problem that seems very arduous. But yeah, so that's the formula. We don't know if it's true or not. Let's prove it. So here's the proof. And we're going to start with the base case, but before we do that, let's just point out to the reader that we'll use induction. And often if you're writing for a mathematical audience, you should still do this, in my opinion. But induction is such a common idea that they'll be able to figure it out. But I like to just point out to the reader usually, what I'm about to do, just to make it easier to understand. So we'll use induction. And then we're going to first look at our base case. So the base case, well, we need to prove that the sum of the first one integers, or one natural numbers, so it's not such a thing as the first one integers, because the integers go to negative infinity as well. But yeah, 1 plus itself, right? So there's nothing else. That's equal to this formula. We need to actually check it for 1. So plug in 1, we get 1 times 2 over 2, which is 1. So it checks out. We've done the base case. Step 2, we're going to assume it's true for k, for some arbitrary k and n. That is, let's tell the reader exactly what we mean. So we're assuming that 1 plus 2 plus 3 plus all the way up to k is k times k plus 1 over 2. I really recommend don't just use n again. Use a different variable. Just it's less confusing that way. So now we're going to show that it's true for k plus 1. Assuming this. We haven't proved that. We're assuming it. So then 1 plus 2 plus 3 plus ... plus k plus 1. What is this? We're going to try to show that you can get it by doing that formula, but we're not assuming that. We're showing it. We're proving it. This is what we're assuming. So we're going to use this freely at some point in our proof, and I think that point is actually right now because I see that right there. I don't like this dot, dot, dot. So let's actually turn this into this. That sum there is a k times k plus 1 over 2, and then we're adding another k plus 1. Okay. All right. Let's do a little bit of algebra here. So what is this? K squared plus k. I never know if I should expand it out or not, or leave it factored, but I know I'm going to have to combine these two. So this is 2k plus 2 over 2. And let's actually add those fractions together. So we got k squared plus k plus 2k, that's 3k, plus 2 over 2. But this is, here, let me come down here actually. So this is k plus 1 times k plus 2. Right, that factors, that quadratic factors there. And we've done it because this is the formula for for n equal to k plus 1. This is the formula. All right. Right. So then we can say something like by induction, by the power of induction. This proves this statement for all natural numbers. And you don't have to write a sentence like that at the end, but it's kind of nice to just conclude it with a sentence. And that's it. And so almost seems, again, like I remember it took me quite some time to really even just believe that this was a thing that you could do. And what could help actually is the various analogies. So my favorite analogy actually uses dominoes. And so move this out. So you've probably done this with dominoes. Set them up like this, and have to be really careful here. Hands can get kind of shaky sometimes, but you can set up the dominoes like this. And the idea is that when you knock one over, it'll all fall over. But when you really think about it, the reasoning for that is mathematical induction, because think about this domino here. I'm going to push this one first, but think about this one over here. How do I know that's going to fall over? Well, it'll fall over if that one falls over, right? So if this one falls over, that will knock this one over, just because that's its position to do so. How I know that one will fall over? Well, I know that if this one falls over, it might not, but if it does, it'll knock that one over, and then I'll knock that one over. So this is really the exact same thing we were just doing with the mathematics on the other page. And this is our base case. Our base case is going to be we're actually going to hit the first domino, and then it's going to knock the other ones over. So that's really that's all that's going on in induction. So hopefully that demystifies it a little bit. But this is definitely something that you're already used to, just in everyday life. But it seems surprising when you actually write up a proof for the first couple times at least. Let's do another example. This is one where it's really important to do several examples. So let's prove a slightly more complicated formula. So let's prove the formula. This is another one of my favorites. So if you have square numbers, if you add the squares, these are called triangular numbers, by the way, like numbers of this form, because you can make a triangle out of them. So 1, 2, 3, 4, etc. They form a triangle. And one reason the sum has to be that is here's kind of a geometric proof. If I take two of those triangles and I put them like this, I turn this one upside down, they sort of fit together. But if I have the first n numbers, that's n, then this is going to be n plus 1. It's one offset here. And the triangle is actually half of that rectangle, so it's n times n plus 1 over 2. So this is sort of visual proof. With the squares, if you add up square numbers, you get n times n plus 1 times 2n plus 1 over 6. A bit stranger looking. And it's actually a really nice geometric proof like that in 3 dimensions, but it's a bit complicated to show. But let's prove it by induction. So it's actually not much harder than the previous one. So proof, number 1, we will start with the base case. The base case in this case will be 1, the sum of the first 1 squared, so I technically should have 1 squared, equals 1 times 1 plus 1, 2 times 2 times 1 plus 1 over 6. What is this? It's 1 times 2 times 3 over 6. That checks out, right? 6 over 6. So there's our base case. And now our inductive step. Assume that 1 squared plus 2 squared plus 3 squared, all the way up to some k squared, equals, what would it be? Just replace n by k. So k is arbitrary. All right, for some k and then natural numbers. Then I might need another page here, but we'll do what we can on here. So what is the goal? I want to show the statement for k plus 1 is true. Okay. Plus k squared. I'm going to write in k squared there because I'm going to use that. See, it's and this is when induction works. Induction works when you can relate the k plus 1 case back to the kth case. And see, we see the kth case as a sub-problem here. So these formulas involving sums. So these are really typical kind of formula you can prove using induction. So this is, well, what is it? I don't know what it is. But I know that is this, right? So I know that is k times k plus 1 times 2k plus 1 all over 6. Oh, but I still have this. So plus k plus 1 squared. And that was the fun part. You do some algebra, and it depends on your definition of fun, but here I feel like I am not so comfortable. Remember, here we had to factor a quadratic, and here I'm worried we're going to have to factor a cubic. So I think I actually want to keep a common factor of k plus 1 here. So let me actually write that first. And then I've got, what, 2k squared plus k, so I multiply these together. And then I'm going to write this as k plus 1 times another k plus 1. Oh, here, I'll multiply by 6 over 6. So this will be 6k plus 6. I'll put a 6 in one of the terms. I'm trying to keep this as a k plus 1 just so that I can factor that out next. So when we add these fractions, we're going to get, my denominator is going to be 6. My numerator, I'm going to pull out a common factor, k plus 1. I get 2k squared plus k plus 6k. That's 7k plus 6 over my common denominator of 6. And then this is, okay, let me get another page. So what is this here? Well, this is k plus 1 times, let me think about this for a moment. I'm hoping this can be factored, so I think it is going to be a k plus either 2 or 3. I think plus 2, and then 2k plus 3. Yeah, that should work. Because we get a 2k squared plus 4k plus 3k plus 6. Perfect. So this is my numerator. And is this what we're looking for? So is this basically this formula with k plus 1 plugged in? Yeah, it looks like it. You can sometimes make that. You can make it look really obvious. So, here, let me do it like this. So I've got a k, right? Or k plus one, right? K plus one, and then I've got a k plus one plus one, and then here I've got a 2 times k plus one quantity, k plus one plus one. Right, that's just a way of rewriting that. See, I'm just making it look super obvious that I have exactly that formula with k plus 1 plugged in, which it is. So we proved it. Well, we proved that assuming it's true for k, we can prove it for k plus 1. And again, we start with this. We can't claim this is equal to anything. Like we can't claim this is actually equal to this. But we can use the fact that we're assuming, and that's what we did. We used the fact that the first k squares, that sum is this, and then just after some algebra, we get there, and that proves it. So we're done. Excellent. So sometimes you have to do a bit of, you have to really find a clever idea or two. So maybe I'll just do one example like that. So example, this will be this is another one of my favorite problems. So it's called the postage stamp problem. Stamp problem. It's a variant of what's known as the Frobenius coin problem. So postage stamp problem is suppose I have. And you can change these numbers, but I'm going to do 4-cent and 5-cent stamps. In infinite supply. I have as many as I need, basically. And the question is, what amounts of postage can I make? What postage can I make? It's actually a rather interesting problem. And so clearly I can make 4 cents. And actually, yeah, let's make a little table here. So 4, I can make 5. Just go down the line here. 8, 9. I mean, obviously I can't make anything less than 4. So 4 is the minimum denomination. But here, I shouldn't do too many. So I can make 4. I can make 5. I can't make 6, right? Well, that's not so hard to convince yourself. I can't make 7. I can make 8, 2 4-cent stamps. I can make 9, 1 of each. I can make 10, 2 5-cent stamps. How about 11? I don't think I can make 11, right? Because I couldn't make 6 and 7. So if I use either kind, I won't be able to fill in the rest. So can't make 11. I can definitely make 12. It's just 4-cent stamps, 3 4-cent stamps. 13, that's going to be 3 4-cent stamps and 1 5-cent. 14, yes. 2 of these, 1 of these. 15 I can make, it's multiple of 5. 16 I can make. 17 I can do 12 and then 5. Yep. And what you'll find is that you can actually make everything else you try. ... So it seems like we can make everything 12 cents and higher. So that's our conjecture. So conjecture. This is like the full process of doing mathematics. You're looking for a pattern. You make a guess. So a conjecture is we can make any amount 12 cents or higher. Okay. And how do we prove it? Well, so let's attempt a proof. And this proof, I don't just want to write it down like the finished thing. I want to really show you how I'd think through this. So, well, there's one reason that it sounds like an induction proof, which is we're trying to prove something for all natural numbers. However, this breaks down, right? So the statement for n is that you can make n cents using 4 cents and 5 cents. We definitely can't make 1, right? So our base case doesn't work. Here's the thing I didn't mention. You don't have to prove p of 1. You just prove wherever you want to start. So if we want to say a statement is true for all natural numbers greater than 12, we're going to make our base case 12. Okay? We're going to make our base case 12. So for our base case, we're going to say, k equals 12 can be made with, let's prove we can make it using these stamps. It can be made with 3 4-cent stamps, right? With 3 4-cent stamps. Okay. The inductive step. This seems tricky. So suppose here I'll just I want to introduce the k right here, so I'll just call this n. So the number 12 can be made with 3 4-cent stamps. So suppose we can make k cents using 4-cent and 5-cent stamps for some k. And now we don't want to say k is any integer because it won't be true, right? For 11, 6, 7, or for any natural number, sorry. So for any natural number greater or equal to 12 is what we really want to say, okay? Greater or equal to 12. And you're allowed to do that. It's just got to coincide with your base case, right? So we're not proving for every natural number. We're starting at 12. Okay, suppose we can make k. Can we show that you can make k plus 1? Well, I'm going to remember what we did to get 13 from 12. The way I thought about that was just take one of our 4-cent stamps and swap it for a 5-cent stamp. So that's easy. Assuming that we have at least one 4-cent stamp, okay? So let's write that up. So suppose we can make k, and now consider k plus 1 cents. So consider, k plus 1 cents. And if the arrangement for k that we know we can do, because that's what we were assuming, if it includes a 4-cent stamp, right? A 4-cent stamp, then swap it out for a 5-cent stamp. Which makes k plus 1 cents, right? Okay. What's the problem? Well, I already mentioned it. Arrangement might not include a 4-cent stamp. If there are no 4-cent stamps, so if instead there are no 4-cent stamps used, then the arrangement for k is only using 5-cent stamps. Okay. And, well, what do we know? K is greater or equal to 12, right? So it's got to be a multiple of 5. So we know that it must use at least, if no, then only 5-cent stamps are used, right? So only 5-cent stamps are used. And then since k is greater than 12, there must be at least 3 5-cent stamps used. See where I'm going with this? There must be at least 3 5-cent stamps used, right? Because otherwise we'd be at either 10 or 5, which are both less than 12. What do you think we want to do with those 3-cent stamps? Those 3 5-cent stamps. We're going to swap those, all 3 of them, for 4 4-cent stamps. So swap all 3 of them for 4 4-cent stamps. Okay, so we turn that 15 into a 16, and so this is going to make k plus 1. Okay. We basically increased our postage amount by 1, so that makes k plus 1 cents. And we're done, right? Because there are either 4-cent stamps used or no 4-cent stamps used. That's it. Yeah. So by induction, any amount. This shows that any amount above. Any amount at least 12 cents, of at least 12 cents can be made. Okay, so that was one where it required a little bit of thinking, but really nice problem, I think. Okay, so this video is a bit longer than I intended, so let's end it here. Then the next one we'll talk about strong induction.